Hey there, everybody. It's Mr. Sheeline here. These notes are just going to be, or this video, I should say, is just only going to cover what's in the notes. I'm not going to go through the check your understandings here because they are decently long, and I just won't have enough space to write on my computer here on the screen to actually to really kind of accurately portray what's going on, and not just that. I guess it's not even just that because I could accurately portray it, but I'd be erasing stuff all the time, and it'd just be a mess. So I'm going to have a separate video for the check your understanding. So look for that. But just keep in mind, though, I still want you to go through the check your understandings. Try to do them yourself. Try to see if you can solve them for yourself, and then watch the video. See how I walk through it, so you have a decent understanding what's happening. But again, that's going to be on a separate video. Okay, so let's just kind of go through this. So friction. So we're getting into friction now, and I know I talked about how I want to get to tension and pulleys, and unfortunately this year we're just not going to be able to get to it, but we've got to cover friction. So what is friction? Well, it's the opposing force that resists motion or a given force in the opposite direction. So, and what this is, technically speaking, it's the friction force is more or less the electrostatic, electronegative forces that are built up between two surfaces. Okay, and friction again always opposes motion or the net force. There are three that we'll recognize, but there's only going to be two that we're going to be, actually looking into and practicing. And it's probably obvious which ones those are. So kinetic friction and static friction, 100%. We're going to be practicing those. We're going to practice on how to find them and how to calculate them. Air resistance, yeah, it's there. We'll say, yeah, we know it's there, and we know that that's going to be a form of friction. But for the most part, we're not going to be calculating that, and we're not going to be practicing with that. Just be aware it exists. Okay. And then friction. Or further on with friction. Sorry, friction is simply a force included on our free body diagrams. Okay, and we apply it to situations where our net force is equal to zero, and our net force is equal to mass times acceleration. Now, something else to add here is that the friction force, and this is a good note to remember, and there's going to be a point in here where that's going to be somewhat mentioned, but keep this in mind. Excuse the bell. So keep this in mind that even if our net force is equal to zero, we still may.
Michael Goff, Daria, Andrew, please go to guidance. Michael Goff, Daria,
ignore
Andrew,
all that. Yep.
Guidance.
Did not expect that. So we still may have motion. Okay. So keep this in mind. Even if the net force is zero, we still may have motion. What we won't have, though, remember, we won't have what? What wouldn't we have? If net force is zero, what wouldn't we have? We won't have, if you thought of it, that's right, we wouldn't have acceleration. So if net force is zero, there's no acceleration. But that does not mean then we don't have motion. So just keep that in mind, something to always be aware of. So here we go. So the two types of friction that we're going to be measuring and we'll be calculating. So there's the static friction and the kinetic friction. So static simply is, and this should be obvious by its name, static meaning, does not move. It stays in one place, no motion. Static friction is the friction that prevents a stationary object from starting to move. So think of it this way. As a concrete example, so your sofa does not move because or at least it doesn't just float around, around your house, because the static friction is greater than any small force that's being applied to it, and that static friction is what allows it to stay put. More or less, it's what you have to overcome to make a body at rest into a body in motion. But then but then something's changed if it's in motion here. But anyway, when it's at rest, it's that static friction that you have to overcome, that it's, that's being applied to it, that allows it to stay there. Kinetic friction is the force that acts against an object that is moving. So easy peasy. And again, it should be obvious by its name. Kinetic, meaning motion, meaning movement. Kinetic friction, so that is the friction that you have to that is continually trying to stop an object that you are applying a force to, or one that's already just in motion. Okay, maybe there is no force that's being applied to it. And just a heads up, the bell's going to be ringing here again shortly. But even if there is no continual force being applied to an object, you still will have kinetic friction trying to hold it back while it's moving. So something to keep in mind: the kinetic friction here. Typically, the kinetic friction here is going to be lower than the static friction. Think of it this way: if you've ever had to move big furniture, like a refrigerator, well, it's an appliance, of course, but let's say, big things like a refrigerator, a really heavy filing cabinet, a sofa, a really heavy TV stand, a table. If you've ever had to move those across a good, amount of space, or even if it's, I guess, even a short amount of space, what you probably notice is that it may take a lot of energy and it'll take a lot of work to get it to move. But once it's moving, you can slide it pretty easily. So think of it in those terms, that the static friction is going to be, typically it's going to be greater than the kinetic here. And that'll make more sense when we get to their coefficients, which we'll get into in the next slide or two. Okay. But the magnitude of friction depends on two things. It depends upon the surfaces that come in contact with one another. And it also depends upon the weight, or realistically speaking, just the mass of the object. Obviously, the greater the mass, the greater force needed to move it. The greater the mass, the more force that will be required, but typically the lower the acceleration that you're able to get that thing going to. Okay. So here's some examples of low versus high friction. So here, of course, you have what looks to be like a hardwood floor. Either that's actual hardwood or it's vinyl, it's laminate, whatever it is. You can see that the texture in here just seems so much smoother, glossier, that you would, if you're wearing socks, you'd probably slip on. And there's the bell, so excuse the bell. And then over here for the high friction, I don't know what this picture is exactly, but whatever the stuff is, probably maybe it's stucco or maybe it's plaster, but whatever it is, it's coarse. There's more surface area, so that means that there's more ridges and areas to where that electrostatic material would accumulate, and just more surface area in general to overcome. But it's a higher, has a higher friction. Now at the microscopic level, this is what we're looking at. So you've got the low friction here with the blue up to the left, where there's less surface area to overcome. There isn't as many ridges. It's seemingly smoother. It's not having all these issues when you're sliding them past one another. But if you notice at the high friction, notice when I talk about surface area, see all these orange ridges, and like that, what that white is empty space, but the orange is the square. It's rough, it's jagged, there's a greater amount of surface area to overcome, and to get things to get locked into, which makes things more difficult to move. Okay. So looking more closely at static friction, this is, the static friction, or the magnitude, the force needed to start a stationary object moving is the maximum static friction. So this is nothing new from what we've already been talking about with static friction. The only difference is now we're adding the word max to it. So the idea behind what the max static friction is that every object has a, dependent upon what it's made of and what surface it's sitting on, will have a particular amount of, or particular coefficient that is associated with the normal force of an object, and also just the friction, the static friction. But the idea being is that static friction will change between 0 and whatever its max static friction is. So as an example, let's say you've got like a little can here, and this can's static friction force, let's say it's equal to 10 newtons. That's its max. And let's say you put so here is the static friction force, and then this is the applied force. So the max will be 10, but let's say you put 5 newtons of applied force on it. Well, the static friction will be 5 newtons. Well, let's change that instead. Let's make it, well, if we put on, let's say if we put on 8 newtons of applied force, then the static friction will pose that at 8 newtons. Okay. Remember, we have to overcome the friction. So at the exact point that we go from a moving or a stationary object to a moving object, okay, so let's say we immediately put 11 newtons of force on here, the max will be 10. But the problem and what's tricky about that is that at the moment that we overcome that, typically we have, or in pretty much all cases, we have motion. And if we have motion, we're not going to be worried about the static friction anymore. But however, at the exact moment before this moves, of course, you would have 11 newtons worth of force on, and the static friction would still be 10. But then again, you'd be working with kinetic once it's moving. But here's something from earlier that I mentioned. So let's say you're given a problem. In this case, well, let's ask, well, what if we have 10? What if it was 10 newtons of applied force, and the static friction is still 10 newtons in the opposite direction? Do we have motion? So because the natural world is quite, what would be the word? Difficult to measure super accurately. Would we have motion if we had an applied force that was equal to the static friction? The answer is it depends upon the question. And it depends upon if we're talking about real life things, if we're talking about practice things in a textbook for a physics class. So typically in the real world, if you were to put 10 newtons worth of force onto an object, and the static friction force was 10 newtons as well, if you maintained that 10 newtons worth of applied force exactly, you would have motion. And that's only because the coefficients in the static friction is not exactly 10. And let's be honest, you're not exactly putting 10 newtons worth of force on. If your applied force is 10.5 or let's say 10.1, and the static friction force is 10.0, you're going to have slight motion. So again, it depends. So if you had a question that said that, you applied so much force onto an object, and then you have to calculate the coefficient, which again, we'll get to the coefficient here in a bit, and they don't give you the static friction force, what you can assume is that and also if they talk about having constant velocity, you can assume that the static friction force will be equal to the applied force. Okay. Because again, here with which I know seems kind of goofy, and it'll make more sense when we get to those kinds of examples, or at least hopefully it'll make more sense when we get to those kinds of examples. But just know the bottom line is you've got to know that it is possible to have motion if your applied force is equal to your static friction force. Okay, so it is possible. So let's move on to the rest of this slide. So if the applied force exceeds the static friction, the object will accelerate. Okay, of course. But again, also remember that little added thing that we just went over as well. So just think about what's going on. Pause the video and answer this question here. Which way is the static friction force acting on this picture? So more or less with this car, where's the static friction force? So pause the video, take a look at it, try to figure it out, answer it for yourself. Okay, and I'll come back and double check with you. Okay, so what you should have said is that, well, we've got this car here, and the static friction force is going to be parallel with the ground, but in opposite direction of where we would expect to see this car move, because we would expect to see it move in this direction, but because of the friction force here, specifically the static friction force, it eliminates, for the most part, it eliminates that kind of motion, and we are left with a good little thing here. Now, real quick, this wasn't part of the question, but also remember, we've got gravity moving down this way, and then the normal force perpendicular to the ground. Okay, so don't forget about all those components of your free body diagrams. So kinetic friction acts as on any object that's in motion. Of course, we've already talked about this. Magnitude of the force trying to slow an object's motion is the kinetic friction. Okay. We blaze through that because for the most part, it's pretty simple. You've got something moving, there's going to be the kinetic friction opposing it. Now, the coefficients of friction. So this is a ratio of the magnitude of the force of friction between two surfaces to the normal force between the surfaces. So again, or at least, or I mentioned this, is that the coefficient is equal to the relationship, the ratio between the max static friction force in this case and the normal force. For kinetic, it's going to be the kinetic friction divided by, or ratioed against the normal force. Okay. Now the ratio, though, depends. It will depend upon the material the material of both surfaces of either the tabletop, the ground, the whatever it is. The surfaces of whatever two objects you're rubbing together is going to affect the static friction coefficient and also the kinetic friction coefficient. And we'll get a sense of that in the next slide. But then, real quick, here is also a deviation from this equation, both of these equations. If we're trying to look for the coefficient, easy peasy. This is what we're looking for. But let's say if we're looking for the friction force, here's a deviation from these particular formulae. Okay, so this is what we're talking about here in this next slide. So, and this is something that actually engineers and other scientists use, mainly engineers, obviously. And especially engineers that are making parts that move, that slide past one another. Try to imagine that, having to be an engineer where you've got to know this. You have to know the coefficients of the surfaces rubbing against one another, because then you've got to know, well, how much force is going to be, how much friction force am I going to have, and then translate that friction force into energy. And the energy you have to translate into heat. And if you've got too much heat rubbing against or forming because something's rubbing against another thing, you're going to have issues. Potentially, unless you're, say, now I'm forgetting, what is it? There's like fusion welding, if I remember, I believe is what it's called, where it's literally robots will it's the only place where you want things to get super hot. I think it's called fusion welding, where you rub two metals together super hard and super fast, and that you have so much heat that they bond together instantly. It's not the greatest kind of welding, and it's used in very specific things, but look it up. It's actually kind of neat to see that. But anyway, so this is when you break these down, generally speaking, this is what it looks like. And notice that they specify, what the material that the object is on. So rubber on concrete, rubber on asphalt, steel on steel, steel on steel, leather, that says leather on rock. But then also notice, this is also really interesting too, is that obviously it changes on the conditions that both of these or either one of these are in. So there's a dry condition, there's a wet condition, there's a greasy condition. So they do take that into account, and that because that will affect your coefficients here, which is pretty interesting. Okay. Now this one, go through this on your own. Okay. Hopefully that was quick enough for you to see the answers. So if you want to go through those on your own, you can, but you gotta go back, pause the video, read what those say, but first answer those questions yourself. Okay, so check your understandings. Remember, I'm going to be doing this on a different video, so that's just the notes here. So I hope this helps. If you still have any more questions, please ask me. If not, then I'll see you guys in the next one.